Hello everyone, my name is Andre and welcome to the first lesson of the School of Solana Season 7. This is already the seventh run of this cohort, so that means we previously had 6 cohorts, so I would say this school is pretty well known in the Solana ecosystem. This first lesson is going to be about the introduction to the Solana, and you may learn also from something from blockchain in general. So, and as you can see, we are educational partners of the Solana Foundation. As I said, my name is Andre. I'm the lead auditor at Ackee. Sometimes I'm the developer, but most of the time, 99%, I'm the auditor. You can see both my Twitter and my Discord handle, so feel free to write me a message if you need anything.
Hi everyone, I'm Joseph. I'm co-founder and CEO of Ackee, and I'm really happy we are meeting here for the 7th time because this is the School of Solana 7, and all this is possible thanks to the grant we got from Solana Foundation. Maybe you don't know what is Ackee. So Ackee, we are smart contract auditors. We are working for clients, but also we love to contribute to the ecosystem. So we are building a lot of open source stuff, and we are doing these educational programs. All this is possible thanks to our clients. So we are really happy we can be working closely with Camino, Marinade, Wormhole, Axar, Aave, Lido, Safe, and a bunch of others. And also we received grants from the foundations. So of course, Solana Foundation, but also in the past, we got a grant from Optimism, from Coinbase. So we are really happy that we can be working in this ecosystem and also giving some value back to you. So regarding the school, I wish you a lot of luck and see you at the graduation ceremony. Bye-bye.
This was a brief introduction from my side, from our side as a company, and now I would like to talk more about the course, more about this first lesson, etc. So you will learn basically what is this course about. All right, so I turned off my camera so we can properly see everything that is on the screen. And now continue about what is this course about. So what you can expect. There is introduction to the Solana blockchain, which is basically this first lesson. Then you will learn introduction to Rust. Rust is the main programming language for the Solana smart contracts. In advance, I would like to say sorry for all of the people who do not like calling them smart contracts, because on Solana, most of the people call the programs actually programs. Smart contracts are more from the Ethereum world, I would say, but I like to call them smart contracts because you immediately know that we are talking about the smart contract. Program can be whatever program, not just Solana. So in this case, I will call them smart contracts also on the Solana. So yeah, Rust is main programming language for the Solana smart contracts. Then we will have 2 lessons, Solana Programming Model 1 and Solana Programming Model 2, where we will talk about basically the programming model as is written there. So regarding accounts, cross-program invocations, basically what is how the instructions of the smart contracts are created, what are the fields, etc. Then we will have best development practices and debugging. We will have also lesson about the security, and then last but not least also about the front end for the Solana programs. So you will learn basically how to connect the front end to the underlying Solana program, or yeah, as I said, Solana smart contract. The second thing that might be important for you is that to aggregate basically everything that is available for you during this course. So we will have YouTube lessons pre-recorded every Wednesday. Then you will do programming tasks. We will have also tasks for the theory, but most of the tasks are programming tasks. What is also important is the community, because we accepted hundreds of new students to this cohort, so you can connect to each other on the Discord, you can chat there, and yeah, do stuff with the community. What is important from our side is the feedback. So you have access to the developers and the auditors ready to answer your questions. So that means as you were invited to the Discord and you received the season 7 role, that means you will be able to write into multiple channels in the Discord where we can answer your questions, from the simple stuff such as how to install this to more complex and advanced stuff regarding the programming model, security, architecture, etc. We also prepared learning materials. You will see on the next slides. There we have QR code to the GitHub repository where the materials are. Learning materials can be also the YouTube lessons. We have created the Solana handbook, so there is a bunch of stuff that you can go through. And last but not least, one of the main tasks during the School of Solana is to let you create Solana project. So when you finish the Solana project, or the Solana project is about basically creating Solana smart contract and also front end for the smart contract. So in principle, you will create the whole app on the Solana blockchain. What is this course not about? So this is not trading course. We are not providing any financial advices. This is not advanced security course, as we have the Solana Auditors Bootcamp, which is dedicated for more advanced developers and security researchers. But this is not. This will be not included in this course as School of Solana. Okay, what are the prerequisites? So we expect that you have at least some basic experience with CLI. These are not recommendations because we did not test everything during the registration form, but this is expected if you do not know how to use terminal. So you should learn this before you start the School of Solana. It is important because most of the stuff that we do on the Solana happens within the CLI. The programming, of course, happens in the code editor, but there are commands that are most of the time used within the CLI. Then there is the basic experience with Git. It is important because for the tasks we use GitHub Classroom, so you should know how to clone, how to commit, how to push to the repository, check out to different branches, etc. It is really helpful if you have any experience with another programming language such as C, C++, Java, Python, etc. Because when you know different language, it is really easy to learn another language. So yeah, and we are going to learn Rust. So if you know, for example, C++, it should be really easy for you to learn Rust because it is just about the syntax. As I said, it is lesson about the introduction into the Solana and the blockchain, but you can see that we expect that you have at least some basic overview of what the blockchain is. For example, you know that there are some blocks, it is chain of blocks, there are some transactions, etc. We do not describe, we do not learn what the transaction is, what is the blockchain, but we learn, or sorry, we teach the basic principles already of the Solana and the blockchain. So the fundamentals you should already know. If you don't know them yet, it is highly recommended to go through the fundamentals first and then watch these lessons and do the tasks. Tasks and materials. So you can see the QR code in the right corner, upper corner. Scan the QR code and you will see the repository where the materials are stored. I think we have also the Docker image there. So if you have a problem to set up the environment, feel free to use the Docker image. Sometimes it might be even recommended. Another thing that we created is the Solana handbook. Again, you can see the a QR code. So scan the QR code and you will see the page where is the Solana handbook. This is just the sum up of I would say some of the most important parts of the architecture of the Solana. But yeah, these are just the fundamentals, introduction into the Solana, because you can always go deeper and deeper. So take this more as an introduction into the concepts of the Solana. Last but not least, there is this young Tolly that I would like to talk about. And who is it? So inspired by the Anatoly Yakovenko. You will learn who is Anatoly in the next slides. Yeah, inspired by the Anatoly Yakovenko, we created this AI agent, which you can use on our Discord in the dev help channel, because during the previous runs there were a plethora of questions towards our side, and that does not mean that we do not want to answer questions. We definitely want to, but sometimes we were slow to answer some of the questions. So if you tag this guy, the young Tolly, in the dev help, you can ask him directly questions regarding the Solana, regarding Anchor, how to install something. I mean, in the context of the Solana and the Anchor, because if you ask him like a random stuff that he will most likely not answer. Yeah, so you can ask him this stuff. He will definitely help you. Most of the time, 99% he's correct. So hopefully this will be helpful. Why is it important for us? Because if you have any question and we are not currently on the Discord active, because I don't know, we are away from the computer, this guy can immediately answer your question. So feel free to use him. It is not necessary or mandatory, because you still don't need to tag him and ask the question. And then when we are back at the Discord, we will answer these questions. All right, now let's talk slightly about the Solana introduction, because some of you might be like newbies in the Solana ecosystem and you just know that there is some kind of token that you can buy, but the token is not the principle of this course. We are trying to ship new developers. So what's the Solana? So it was founded in 2017 by Anatoly Yakovenko, and he's a former Qualcomm engineer. At the 2018, the testnet was released, and at March 2020, mainnet beta went live. So as I said, there is this expectation that you already know what is blockchain. So the mainnet is basically something like the main network where all of the assets have the value, and testnet is like the testing network, testing blockchain, where the assets are basically worthless, and is dedicated for developers to test their smart contracts before shipping to the mainnet. Also for testing new features that are going to the mainnet, like from the architecture perspective of the Solana. Like the Ethereum or also Bitcoin, it is layer 1 blockchain. I said Bitcoin, do not compare directly to the Bitcoin network, because as far as I know, you cannot do such complex stuff on the Bitcoin as you can do, for example, on the Ethereum and on the Solana. So the Ethereum and the Solana are smart contract based blockchains. On the Bitcoin, the main principle is basically store of the value and the token called Bitcoin. Similarly to the Ethereum, it is also proof of stake network. So you may know that there is, for example, Bitcoin, which is proof of work, where there is every miner needs to find some nonce, which will result in some kind of a hash, which need to make some kind of requirements in order to be valid. So that's the proof of work. On the other hand, proof of stake, you take some amount of assets, you stake the assets, and then you validate and create new blocks. When you create new block, you are rewarded. When you vote as a malicious validator for a validity of a block, you are punished and some of the stake is taken from you. as I said, Ethereum is also proof of stake network. So this Solana, this picture is basically taken from the turbine and Helios. I think this picture actually really nicely describes the I would say also blockchain as a whole, but we are talking about the Solana. So as you can see, this outer layer, these are just computers, mobile phones, web applications, etc. So for example, the Phantom is a mobile phone app. All right, so the Phantom would be in this outer layer. Then you have this layer in the middle, which consists of the RPCs, and then you have this middle part, which consists from the validators. So the Solana, we can say this also about the blockchain, but the Solana is basically decentralized, globally synchronized state machine. So if I go back, that means these validators are computers, servers, which have some kind of software on them. And the main principle is to keep the software synchronized at all costs. Okay, so every validator in this middle part should have its software synchronized with other validators. So that means if this validator does something on its software, so somehow changes the software state, so it can be like, imagine the Google Sheet table and you add a new row to the table, so that's the change to the software. So if the change happens or occurs on one of these validator, the synchronized state machine means that each of the validators should have the synchronized state, so this change should be propagated to all of the validators. And then, as I said, there is this middle layer, which are RPCs. So these are similar nodes as the validators, but they do not vote on the validity of the blocks. So that means this is like the storage, for example, for the data. So if you have this web app and you want to know what is the balance of some account, you do not talk directly to the validator, but you can talk to the RPCs. That's the storage. So in principle, the RPC has more data. As I said, this is from my point of view, this is a really important statement, the centralized globally synchronized state machine. So if you understand this statement, you basically understand Solana. You can see two links there. So if you would like to visualize, for example, how the Solana works daily, basically, you can go to the first link, validators.app, and you will see how all of the validators change at a really fast pace. So this is, from my point of view, really nice visualization. The Solana beach, you can see basically all of the validators from the highest stake. Then there is this cumulative stake. You can see what is the Nakamoto coefficient. And yeah, so this is, from my point of view, nice visualization too. You may heard that there are innovations in the Solana ecosystem, such as proof of work, proof of history. Proof of work is on Bitcoin. Proof of history, Tower Byzantine fault tolerance, and there are a lot. All right, so Turbine, Gulfstream, Sea Level. From the feedback for the previous cohorts, we learned that people don't want to hear just the terms. They want to understand what basically each of the term does. So we took this feedback, and in this lesson, I will try to describe what most of them, because it wouldn't fit in 1 hour or 1:30 a long lesson. So most of the terms I would like to describe, but some of the terms we will not describe in this lesson. But I still think you will learn a lot from the Solana perspective at this first lesson. Before we jump to the description of the concepts, where we are now. So currently we have Nakamoto coefficients 22. For those who don't know what Nakamoto coefficient is, so basically it is the smallest number of validators which should cooperatively work together to halt the network, let's say. What does it mean to halt the network? There are multiple levels what you can do with the networks. First thing is that you can halt the network, so it will stop. The second thing what you can do with the network is that you produce malicious informations on the network. So for example, Alice and Bob 10 bitcoins might be malicious transaction if that not happen. So these are basically two levels of what can happen on the network. Nakamoto coefficient talks about the first level. So just that the network will not work, which is like the network is paused. The second level is much more critical. For that you need I think 66% of the stake. That's really huge amount. So Nakamoto coefficient just talks about the first. So you need to 22 biggest validators. I'm not sure if I said biggest. You need 22 biggest validators to cooperatively work together to hold the network. On the Solana, there are 1,000 to 1,300 true TPS transactions per second. There might be this information about the true TPS, the word true. It is just a small difference because if you open, for example, the Solana Explorer, you may see something like 4,000, 5,000. Within this 4,000 TPS, there are also included vote transactions which happen between validators to vote on validity of blocks. So it is important to distinguish between these two. So true TPS means basically just transactions from, let's say, users, bots, and not the vote transactions between the validators. But I would say 1,300 transactions per second is pretty nice performance, and this is also increasing because we are trying to increase bandwidth and reduce latency. Block times on the Solana are 400 milliseconds. For example, on the BTC, you have approximately 10 minutes. So that means each 400 milliseconds, new block is created. On the BTC, approximately each 10 minutes, new block is created. There is this time to finality, which is approximately 12 seconds. That means after this period of time, it is really unlikely that the block that your transaction was included in is not valid. This can occur due to forks, for example. This is not that important to talk about, I would say, in this lesson, but yeah, there might occur forks. You may know from I think it is much simpler to describe this behavior on the BTC, where you can have multiple basically branches of the chain, and there is this rule that the longest branch is taken. So for example, your transaction is in the block and this block is in the branch, it is in the forked state, and it is in the branch which is shorter. So that means this second branch will be let's say reverted. So, and the second branch will be taken as valid. Approximately 1,200 validators currently. I would say maybe in the previous picture there was bigger number. Yeah, the number was decreased slightly because during the changes from the Solana 1.18 to the Solana 2, I noticed that the number of validators decreased. But what is more important, I would say, is, for example, the position, the geographical position of the validators. So it is much more valuable if you have 1,200 validators across all of the countries than to have 5,000 validators in, for example, one city. All right. So but this number will, I would say, grow in the future. Solana has multiple validator clients, which improves decentralization. Why is it important? As I said, there is this software which runs on the validators. And to increase also the decentralization, there are multiple factors you can do. The most simplest one is to increase number of validators, but it is also important to improve the software that is running on the validators. And what is also possible is to create like multiple implementations of the software that behaves basically the same. And that is what is happening in here. So instead of having just the one software that runs on all of the validators, we have multiple clients, multiple softwares, let's say. The first one is Ackee, then you can know Jito or Firedancer. There are multiple another in development currently. Why is it important? Because the simplest example, let's say the Ackee client has a bug. And let's say you run the Ackee on all of the validators. So in that case, every validator needs to fix the bug on their client, on their computer server, or let's say. If you have multiple clients, if the bug occurs only on the Ackee, then the validators who run Jito Firedancer can still work, and that means the blockchain can still work. What will happen is that Ackee will fix the bug and will synchronize again with another validators. So that's the simplest example. Let's now talk about how the blockchain, how the Solana can be so fast so it can process, for example, 1,000 transactions per second. So the main principle that we, as I said already, that we try to achieve is to increase bandwidth and reduce latency, and that's it. That's why is the Solana so fast. But actually, no. This is why is Solana so fast. And yeah, you can see some of the terms that I showed you on the previous slide regarding the new concepts or the innovations in the Solana ecosystem. So on this picture and on the additional slides that are after, I will try to explain my best what are the main components that ensure that the Solana can be so fast. So let's talk first about this picture. So you may already, for example, use for software or Phantom. This is the most simplest example from my point of view, because the Phantom, you can just transfer your funds to your friend. You have the USDC in your wallet, or you have the Solana in your wallet, and you can transfer the Solana, the USDC, for example, to your friend, to, I don't know, some market when you go buy stuff, etc. So what is happening basically under the hood? So you have this wallet with $420. In this case, we can say that's the USDC. You have this decentralized application or the app, or let's say the wallet. So you are basically in your wallet, or in this case, you are already connected in your wallet. So disconnect is not that important, but let's say you have the decentralized application. You connect your wallet within the decentralized application. You say in the app that you want to send some funds, so you will receive transaction from the decentralized application. Then within your wallet, you sign the transaction with your private key, and then the transaction is sent from the app to the basically RPCs that you could see in the picture where we had multiple layers, to the RPCs, and from the RPCs the transaction is forwarded to the validators, so the transaction can be validated, and actually the amount of dollars can be actually transferred, or whatever action you decided on in the app can be actually executed on the blockchain. What is the next step in the validator? When the transaction is already forwarded to the validator, there is this one validator which will produce block. So basically the transaction goes from the RPCs for simplicity. It is fetched, the signature is verified, so the transaction is valid. Then we have this middle part where the transactions, because there are multiple transactions, not just yours, the transactions are processed or executed on the validator. This is what might be important here. The transactions change the state of the client. As I said, the Solana is decentralized state, globally synchronized state machine. So the transactions actually change the state. So you said that you want to transfer funds from your wallet to the wallet of your friend. So that means you are changing the state of the blockchain, because the funds will be transferred from you to the friend. And then there are multiple transactions because multiple people interact with the Solana. And what can Solana do is to process the transactions in parallel. You can see this within this rectangle, that there are like multiple layers, and each layer can basically process the transactions. So that means the transactions are processed in parallel. That ensures fastness, let's say, or the good performance, the fastness, the nice transaction per second output of the Solana. You can see there is this proof of history service, and there is also bank or account DB. So the first thing which is important is that it is called proof of history, but it is not consensus mechanism like proof of work, for example, okay? Or proof of stake. So proof of history is synchronization mechanism. The second thing is the accounts DB. So in all of the validators, there is something called storage. You may know this from for example, EVM from the Ethereum, where there is one storage for the smart contract. On the Solana, we don't have such thing that smart contract has directly storage within itself, but we have something called accounts. So imagine it like this. You have the smart contract on the Solana blockchain, and you want to interact with this. You will definitely understand this in the upcoming lessons if you do not understand it yet, because you will basically see how the smart contract works, and you will see basically the principles that I'm going to describe in the upcoming sentences. So if you are maybe if you feel a little bit lost for now, you will definitely understand this later. But Solana smart contracts do not have the storage directly within themselves, but on the Solana we have accounts. Each account is something like a key value pair. So imagine this from the different programming languages, something like the hash map. All right. So you take some key. It can be number. This number is hashed. The hash is unique, and this unique hash is put into the hash map where it has corresponding value. On the Solana, it is similar, and you have accounts DB where the key is actually public key, or the public key which you also see in your wallet. And this public key is basically the key in the hash map, and there is corresponding value which are contents of your accounts. On the Solana, there are multiple type of accounts. So for example, the first is the simple wallet, which just hold assets, as you can see in your wallet. That's the simplest account, I would say. Then, as I was talking about the storage, there are data accounts which hold data. So if you have smart contract and you want to store data somewhere, you do not store them directly within the storage of the smart contract, but you store them within the data accounts. And when you implement the smart contract, each instruction supported by your smart contract needs to have defined what accounts it expects on the input. So in the smart contract, you can take these accounts and then store the data within the data accounts. As I already said, if you feel a bit lost, you will definitely learn this in the Solana programming model, because we will develop the smart contract, and you will see the accounts on the instruction inputs. And so that's the account DB. There are also additional account types on the Solana. So for example, there are executable account types. So in principle, your smart contract is also stored within account, but this account is marked as executable. All right. When the transactions are executed, they are basically broadcasted to the other validators. What is happening here is that you take the transactions which change the state of your client, which is running on your validator, and you put them into the block. And then you broadcast this block to all of the another validators. And the validators vote on the validity of the block. That's this broadcast stage and this turbine stage. So you are this validator and you broadcast basically the block to all additional validators. And there are such things such as neighborhoods. Sorry. So you do not directly broadcast the block to, let's say, each validator, but for example, you broadcast the block to your neighbor, and your neighbor broadcasts this block to another 3 neighbors. Each of these 3 neighbors broadcast the block to another validators, and it has this tree structure. All right, let me drink water. So what happens next is that every validator received the block that you created as a validator. As I already said, the transactions within the block change the state, and in order for all other validators to have synchronized state with you, all other validators need to execute the transactions the same way as you executed them. So that's basically this block validation. That's the main principle, I mean, in this point. And then the consensus is reached. What I would like to talk about is also the proof of history, so you understand why is it important. What can happen here is that you as the validator process, hopefully you can see the mouse, yes. You as a validator can process the transactions, but what ensures that the transactions are in the correct order in the block? Because they can be created, processed here, executed there, and then in the different order put in this broadcast stage, and put in the different order put in the block, which is in the broadcast stage. What ensures the correct sequence of the transactions? And that's actually the proof of history. So in the proof of history, I have a slide about this. So I don't think it is necessary to talk about it right now, but just remember that the proof of history is important to keep the correct sequence. In principle, within this one part, the validator creates the sequence for the proof of history, and then where the other validators receive the block, they can verify that the sequence is correct. And the difference, which also is part of the good performance of Solana, is that this validation can be done in parallel, and this production of the proof of history is sequential. So this can be always, because it can be done in parallel, this can be always faster than the creation. All right, that's the introduction to this picture, and I would like to now talk about more depth, but yeah, I already did for some concepts. I would like to talk into the more depth about some concepts. So the first thing is that I would like to talk is the Gulf Stream. So that's this part, all right? So you may know from the other blockchains that there might be something like the mempool. So I think Ethereum has mempools. So that's basically something like pool of all the transactions, and the validators just take the transactions from the pool. On Bitcoin, I would say it works the same. Let's say you have really you enter into the Bitcoin transaction that you want to pay really big fee to the validator or the miner in that case. So that increases the likelihood that your transaction will be picked really fast. If the fee is really low, that decreases the likelihood that the transaction will be picked. But this is not important on the Solana, because on the Solana there are no mempools for transactions. What is, on the other hand, happening on the Solana is that this is the validator. We on the Solana have something called leaders. So there is this leader schedule for next 2 days. That the leader schedule means for the next 2 days or for the next epoch, which is approximately 2 days. Each validator is selected to some slot. Slot is just the smaller portion of the epoch. So slot has 400 milliseconds. As I said, the block time is 400 milliseconds. So during each slot, the block is created. The block is created by the leader, and the leader schedule is created for the epoch in advance. So before the epoch starts, the schedule of validators that will be leaders in the epoch is pre-computed. So that means in advance you know what is the who is the leader. So, and what is happening in the Solana is that instead of picking the transactions from the mempool, each transaction is directly forwarded to the leader, because all of the validators, as I said about the leader schedule, all of the validators know the leader schedule, the pre-computed sequence of validators that will be leaders. So they know to whom they should forward the transactions. So that's the Gulf stream. This increases the performance, because instead of for the transaction waiting in the mempool, the transaction is directly forwarded to the validator. So you can see it here. So this is the DApp. From the DApp, the transaction goes, for example, to the RPCs, and from the RPCs, it goes to the validators. But this validator is not the leader, so this validator forwards the transaction to the leader. So that's the basic principle. What you can also observe in this slide, and what happened, I would say, last year, which is 2024, at the spring, was the congestion of the network. And at the time, something like stake weighted quality of service was introduced. And what does it mean? So instead of everyone having basically the same likelihood of lending or forwarding the transaction to the leader, because the congestion was about that a lot of bots, a lot of spammers, a lot of machines were sending and spamming transactions to the leader. All right, and the machines, the bots can definitely spam the transactions faster than users. So if some bot sends 10,000 of transactions per, I don't know, 10 seconds, that's much faster than you sending the transaction from your wallet that you want to transfer funds. So the server, the bot, has the bigger likelihood of landing the transaction. So you actually were not able to land the transaction. So as I said, the stake-weighted quality of service was introduced, and what it does. So you can see there is this leader, and based on the stake of another validators, the leader has some amount of connections with that validators. You can see there is this 80 and 20%. So, for example, 2,000 connections are dedicated to these staked, more trustworthy validators. And there is this 20% or 500 connections which are dedicated to the non-paired RPCs. What that means? That means if you have validator from the best known validators, let's say the Helios, Everstake, I don't know, my thing, Lido is also there, Rockaway, etc. These validators hold a lot of stakes. So that means that's the higher likelihood that they are trustworthy and they will not spam transactions. So what was introduced is that based on the stake, there is this number of connections which can be used on the leader to receive the transactions, all right? And apart from that, what can happen is that the validator can also delegate its stake to the RPC. not directly delegate, meaning that the stake is transferred, but they can just appoint some RPC that, yes, I'm the trusted validator, but I also trust this RPC. So this RPC can also directly forward the transaction to the validator. So instead of, for example, going the transaction through this validator, the transaction can go directly to the leader because the stake from this trustworthy validator is delegated to the RPC. Of course, there's remaining 500 connections, which can be from the non-trustworthy validators or non-trustworthy RPCs. I don't want to say that these are non-trustworthy, let's say non-paired. So that means they are not necessarily need to be malicious, but they are just not paired. So, but they can still send the transactions to the leader. So yeah, this was the Gulf Stream and the stake-weighted quality of service. To sum it up, this is the app or the user, the wallet. The transaction is forwarded to the RPC, from the RPC to the validator or directly to the leader. And this is the stake-weighted quality of service, which basically allows trustworthy, more staked validators to have these dedicated connections. And then there are non-paired RPCs and validators which have just opportunity of 500 connections. So that's basically it. Just a quick addition to this, on the network layer, Solana uses Quick, which is something similar to the UDP. So this also increases the performance of the Solana. You can see the TCP, which also has the longer handshake, let's say. On the other hand, Quick handshake is shorter. The Quick can reuse connection information from the previous connections, etc. You can also see that the TCP connection is more strict, I would say, or sequential. So basically, you send the message, then the message that the message was received is sent back, etc. Whereas from in the Quick, you just take the message and everything sent to the server. For example, you may know UDP from, for example, streaming, such as Twitch, for example. So basically, the client just sends all of the message of the data from the stream. So the stream basically the video is good, and the audio is also good. All right, processing transaction, or in other words, building blocks. So let me go back to this picture. We skip basically this part because this is simple. You just you just want to transfer funds, so you click on the transfer. That you enter $20, you sign it, and then the transaction is sent. That's the first part. Then we were talking about this Gulf Stream, and now we are going to talk about this block building. Okay, so this you should already understand this. These are the validators. So that's basically from this part where the leader and the transactions are going to the validator. So on the network interface, you fetch the transactions, or in this case, these are just the packets at that point. You have a look into the packets, and you know that these are there are transactions within the packets. So you first thing that you do is to verify the signatures, because if the signature is invalid, you can filter a lot of incorrect or malicious transactions. And then you take this filter transactions and you send them into the banking stage. Here, here are basically 3 points that I would like to talk about. The first is, how is it possible to process them in parallel? Then we have this bank stage, or accounts DB, and then we have the proof of history. And there is this broadcast stage and the turbine, which you could see also on the slides before. So the first thing is, how is this possible to be processed in parallel? So that's really simple, I would say. I was talking about the accounts, and you will see this in the programming tasks, but you need to specify the accounts that you want to use within the particular instruction of your smart contract, you need to specify the accounts. What you also need to specify is that which accounts are going to be mutable. So which accounts you just want to read from, or which accounts you also want to modify. So just for the example, if you have a transfer instruction that you are transferring 20 USDC from your wallet to your friend, your wallet needs to be mutable and your friend's wallet needs to be mutable. So that means you can update the states of the accounts, update data within. And this is important for the parallel processing, because if you have a lot of transactions and you want to process them in parallel, you know what accounts are within the transactions, because the transactions consist of instructions, and you know what accounts are in there for the instructions, and you know which of the accounts are mutable. So in that case, you can create order of the transactions such that there are no any conflicts, such as read after write, etc. Because what can actually, or hazards, let's say, because what is important is just to ensure that during the parallel processing, there are no two transactions or two instructions which are processed in parallel, but both update some account state of the one same account, because you don't know which update should happen first, if the instruction number 1 and the instruction number 2, or the instruction number 2 and the instruction number 1. Same can happen if you have, for example, read and write, right? But the write after write is more simple to understand, and you don't know this. So there is this, I think it is called scheduler, which can actually read this data from the transactions and create correct order of the transactions and put them into the multiple processes, so the transactions can be processed in parallel, because the sequencer, I'm not sure if it's called sequencer, but hopefully it is. It is scheduler. So the scheduler knows which accounts are going to be mutable in the transactions and which are just read only. And if you are reading from the accounts, it is completely all right, because you can read from account in instruction 1 and instruction 2, and also in instruction 2 and instruction 1, because the behavior, the order is not important, because you are not updating the state of the account, right? So if there is 5 Solana in the account, it will be 5 Solana if you have instruction 2 in instruction 1, or vice versa. So that's the main principle why the transactions can be processed in parallel. And then you have this broadcast stage and turbine stage. All right, now let's talk about the proof of history. So yeah, as I said, this proof of history is important, and I think I have it on the next slide. Yes, the proof of history is important for all of the validators to synchronize, or to know, to validate if the transactions in the block are in correct order. Yeah. So for the example, imagine that you have newspapers, all right? Just newspapers, and in the newspapers there is photograph of an apple. What you can say is that the photograph of apple was created before the newspapers was created, because in the newspapers there is actually the photograph of photograph, all right? And that's basically what is happening here in the proof of history. You have multiple transactions, let's say thousands of transactions, and you create, after each transaction you process, you create some kind of checkpoint. In this case, it is called hash. So most of you might already know this. this term. So you create some kind of checkpoint, and then you use this checkpoint to create another checkpoint after second transaction, and you use this checkpoint to create another checkpoint after third transaction. And what is important is that if you change the order of transactions, the checkpoint would be incorrect. So let's talk about this on this slide. So you have this entry queue, all right? So this is transaction. This little square or rectangle is transaction. So you take this transaction and it goes in here. You have this rectangle. Let's forget about this part, this left part here, and you have this rectangle. And as I said, this is something like checkpoint, but I already mentioned the hash. And this is hash. The hash is just a random string, not completely random, but it looks like a random string of characters. So you use this checkpoint. It is also on the input here. And this was the input, the transaction. And from these two inputs, you create new checkpoint, okay? And that's basically it. Because on this, you can create such, I don't want to say blockchain, it is just a sequence which you create in this part where you process the transactions, all right? And when the block is broadcasted to other validators, also this sequence is broadcasted. So instead of other validators to, I don't know, messaging to the leader about, yeah, hey, was this transaction processed between this transaction or after, the leader just create this sequence of the checkpoints, and the other validators can validate that these checkpoints are correct because they have the sequence of the transactions basically in the block the leader broadcasted to them. So that's the main principle of the proof of history. What is also important to mention, I think I'm trying to describe this as simple as possible. If you understand somehow the proof of history, I think this can improve your understanding, but I still also recommend to read about the technical concepts of the proof of history, and I think this can clarify like more stuff. What you can also find in the resources is that the proof of history sequence can be or needs to be created in sequence or sequentially, and can be validated in parallel. Why is it so? I said that there are these checkpoints which are used in another. You can see you have this checkpoint, and this checkpoint is input for the creation of this checkpoint. So that's basically why it needs to be created sequentially, because you cannot create checkpoint number 400 if you do not have checkpoint number 399. So yeah, you cannot create this checkpoint, this box, if you do not have this box, because this box is input here. However, if you already have all of the boxes, because as I said, this is also broadcasted to other validators by the leader, if you have all of the boxes, what you can do is that you can validate them in parallel, because one thread can start at the validation here, take this thing, they have the sequence which is here, which is behind, because you already have all of the checkpoints. So you can use that for validation until this point. And from this point, there can be also another thread, the second thread, so the parallelization. The second thread, because you already have all of the previous checkpoints. Okay, so yeah, that means you can you need to create it sequentially, but you can validate it in parallel, so that is faster because you can use multiple threads to validate it. And that's the main principle of proof of history. And before we continue, I think there is just the Alpenglow. Before we continue to the Alpenglow, last point that I would like to briefly touch, but I already was talking about the accounts. Yes, so you can think about the accounts such as this is the bank. And as I said, the accounts are just the key value pairs. So you have this key and to the key there corresponds value, which are in this case bytes. And you probably don't know yet SPL token account, but this is just the token account. This is just the account which holds your balance of USDC. And this account has multiple fields. So the mint, or in other words, the token it corresponds to. So the address of the USDC, the owner, which is your wallet, the amount which it holds. So 200, for example. Then there is this delegate, because you can delegate some amount of your USDC to another entity. There is this amount delegated, and if there is any authority to close the token account holding the USDC, these are, let's say, in this case, not important. But what is important here is not to understand the layout of the SPL token. The important is that this is basically the value. So you have this address, the key, which is the public key, which is also public key of your wallet. You can see this in the Solscan, for example, or Solana Explorer. And corresponding to the key, you have these bytes. And these bytes, or this structure, is stored within the bytes. There are additional metadata which are stored in the bytes, not important right now, but these are bytes of the SPL token account if there is SPL token account on that address, because there might be different type of accounts stored on that address, so different type of data in the bytes. Yeah, here is also the mentioned public key. Hopefully this clarifies stuff. Just keep this in mind. What is important from the account perspective is that smart contracts on Solana do not have dedicated storage within the smart contract, but they use accounts. You will learn more about this in the programming, where you can practically see how it works. All right, and yeah, there is this term called Alpenglow, which is new innovation on the Solana, and I would like to briefly talk about it because it will be released in the, I would say upcoming months, and I don't mean like 2 months, I would say 2026. Yeah, first I heard about it on the Accelerate in the New York City, so I would like to talk about it during this first lesson. So let's continue. All right, so Alpenglow, which is still kinda new to me, so hopefully I will describe it correctly, and yeah, we will definitely not go into like a lot into depth. So yeah, I will briefly tell you what I think or what I read it should be, it should do, and the new concepts. So yeah, with Alpenglow, the time to finality should decrease to 150 milliseconds. Currently, if you can remember, early in the presentation, we were talking about 12 seconds right now, so it should be decreased to 150 milliseconds. There shouldn't be both transactions anymore. I think I was talking about this also during the transactions per second and difference between true TPS and the TPS as a whole. This in principle means that there are currently on the Solana, the votes on the blocks for the validators are also on-chain as the vote transactions. This shouldn't be the case anymore with the Alpenglow. What will happen is that when the validator receives, or I will tell it later because I have a picture to compare it to the current architecture. There shouldn't be proof of history anymore, or at least in consensus, because I was talking about the proof of history in a perspective for the order of transactions, but this proof of history mechanism is used also in the consensus because there are periods such as lockouts, so validators cannot immediately basically vote on the forks. So yeah, that means from my point of view, at least from the perspective of consensus, there shouldn't be the integration of proof of history anymore. I think the proof of history will be removed completely, but I'm not sure. You can read through it and make your own consequences or conclusions. Sorry, conclusions. Yeah, but that's not that important. Importance is that the proof of history will be removed from the consensus. And yeah, what is the consequence from no more vote transactions? For example, is that validators, as I said, the vote transactions are basically on-chain transactions, so they also have fees. So small validators will not be required basically to pay fees because the vote transactions will not be on-chain, so the expenses will be lower. There are, yeah, there might be more concepts like new to the Solana ecosystem, but for now, I understand it that there are two main components, which are rotor and votor. And yeah, that's it for this slide. I have my sources there, so you can definitely go to the Helios blog and read about the Alpenglow in there. So let's now talk about the I don't know how to say rotor, and then we will go to the voter, and then I would like to make the comparison. So the rotor is basically update or change in the turbine. So if you can remember, we were talking about turbine, that's the block propagation. So the block propagation had basically tree structure. So that means the block was propagated from the validator, sorry, from the leader to another validator, and from that to another validator, etc., based on neighbors. What should happen with the rotor is that you can see that the leader basically sends the block to the, I think they are, yeah, they are called relayers, to the relayer, and then from the relayer to another validators. It still has some kind of tree structure, I would say, but it is not that multi-level tree structure. So it is just from this leader to the relayer, and from the relayer to the to another validators. I would say there will be multiple relayers. So yeah, that's from my point of view, basically the main idea of the rotor. What I forgot to mention is that some of the things that I mentioned here might be still concept to change. So I'm not sure how final these changes are, but I'm sure that these changes are not on the mainnet, but and I would also say not on the testnet yet. So some of the things that I'm talking about right now may change in the future. I'm not sure how it is likely. Okay, then there is this second term, which is Volter. And what will happen is that instead of basically other validators voting on the block and waiting for the finality, which is 12 seconds currently, what will happen is that they will vote on the block, but there will be some kind of aggregator which will aggregate all of the votes, and in principle the votes will not be on-chain. So basically we will have this validator. The validator sends the vote information, not transaction, because I don't want to say that it is on-chain. This validator will send vote information, vote message to this aggregator. Maybe there will be some mempool. I'm not sure if the votes will be like direct to the aggregators, but this vote message will be sent to the aggregator. The aggregator, you can basically see it here. These circles are validators, and yeah, there is this pool. So most likely there is going to be some kind of pool, and these validators basically send both messages to the pool, or let's say to the aggregator. And when the 80% of stake reaches yes, then we have this fast finalization, and we have this BL certificate, which is like the signature that 80% basically voted yes. And this think this certificate, this BLS certificate, is sent to the next leader, and a hash of it or some signature of it is included within the next block. So in principle, not all vote transactions will be on-chain, but just the certificate, just the final vote, which consists of all of the signatures of the validators, or I mean, the 80% stake, will be included. The aggregated certificate will be included in the next block. Then there is the second option, which is slow finalization, and I would say that's the principle where not 80% is reached, but 60% is reached, and that's this slow finalization will, I would say, happen in 2 rounds. So you will have this first round, which achieves the 60%. No 80% was reached, so just 60. So for that, we will have the second round, and if the 60% is reached also in the second round, in that case, I think the block is finalized. If not, then I would say it is skipped. So that's how I understand it so far. And based or compared to the previous description of the Solana, so this remains basically the same. I would say the Gulf Stream will remain the same. This might be changed due to the proof of history. So maybe if I get it correctly, because I said the proof of history should be at least removed from the consensus. I think it will be removed also from there, so there is not going to be any more the proof of history during the block creation. This is the rotor part. So instead of having turbine, we will have just the part of it. So instead of having this multi-layer structure, there will be something like leader. From this root node, it won't be called root node, but there will be multiple relayers, and from the relayers, the blocks would be directed to all additional validators. And then from this point, I think the gossip service, which was dedicated to the votes right now at the current stage, I would say, then this will be replaced, I would say, by the voter, and also there will be likely changes in the consensus, maybe. I'm not sure, but yeah. Basically, this validator will, instead of sending the vote transactions on chain, will send his signature of the block, as we had here, the signature of the block to the aggregator or to the pool, or how to call it. And then if there is at least an 80% of stake vote yes, then we have the fast finalization. This will happen off chain, and what will happen on chain is just the finalization, and the certificate will be included in the next block, so it will be redirected to the next leader. That's how I understand it. So yeah, feel free to have a look at the Helios block that I linked here. So Helios, the dev block Alpenglow. And that's basically it for this presentation. I hope that you enjoyed. I hope that you learned something new, or at least there was some additional clarification to most of the concepts in the Solana. If you have any questions, don't forget to ask Tolly. So as I said, young Tolly on the Discord in the dev help, but yeah, of course, ask us, me, Matej, and another guys from our team. So yeah, that's it. Enjoy the rest of your day and see you at the next lesson. Bye.